In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality.
All right, Toby, we're live if you want to roll us in.
Excellent. So thank you everyone for being here for Aether Roundtable number 31. Tonight we are going to be having Shane present on Sky Miles. This one has been a while in the making and I think quite anticipated by a number of us here. So yeah, really looking forward to it.
Yeah.
Shane, are you back yet, my friend?
No, not. I just read DMs. Not even close.
Oh, okay. So we are live. We're gonna have to
Yeah,
a little bit of time
there's
here.
going to be a short intermission here. Stone's going to hop on the saxophone and play a little ditty.
That'll be awesome.
I kind of did what I have in mind. It's not something to play, but to present. I don't know. It's a little Dewey I did years ago when I lived in New Zealand. Still, it was a takeoff on my favorite things. You know that one. It's all written in 3. It's a cute little waltz. Some of my favorite things. It was something I redid in 11. So it's kind of like 3/4, 3/4, 3/4, 2/4 time for those people who are musically educated.
Ooh, yeah.
Yeah, it's a cute little swing uppy downy thing. I just wrote it as something that would repeat after a few seconds, so you could use it sort of like an intro theme, and which is actually something my wife is using for something else she's doing online when people show up at her Zoom meetings or whatever, in the lobby, wherever you might be. That's the tune you hear. I gotta dig that up for you guys, that's for sure, rather than just freaking talking about it all the time.
Yes, please.
Yeah, that'd be neat.
So another thing, just real quick while we're waiting, I don't know if you guys heard, I was recently reading about some Greek history from some sources, and some sources were telling me that according to some sources, there was a guy named Cryptosthenes, and back in 214 BC, after he witnessed a Selenelian eclipse where the sun and the moon were in the sky and the moon became eclipsed, he then decided to use some sticks and shadows, and he used sticks and shadows to determine that the objects in the sky were in apparent positions and that the earth is definitely flat. So just so that you guys know, according to some sources, there's a source of Cryptosthenes who measured the earth to be flat, an ancient wise Greek man. Wow.
I read that on Twitter today, that Cryptosthenes, not only did he measure that flatness and determine, the apparentness of the sky, he also, during the eclipse, he boiled some water, and based off of how long it took for the water to boil, he determined his longitude. And from there, he also measured the sun's ecliptic plane and the moon's ecliptic plane, and came up with the instruments to do that. But unfortunately, those are lost to history. But we do have some memoirs from a guy who worked at the Librarian of Alexandria. He is the janitor, and he knew that guy. He talked to him like a little bit. They used to be boys, and he told him about his ventures measuring the sun.
Yeah, so we have sources that have given us some sources. And so on top of that, not only do we have sources that have given us some sources about Cryptosthenes, but also the claim of Cryptosthenes and his measurement of the earth to be flat has never been debunked. So there you go.
Wow. Huh. That sounds very scientific. And again, ladies and gentlemen, we do apologize for this delay. It would, hopefully Shane finishes with the thing he's doing very soon.
Let's see here. In the meantime, I'm going to look at some of these historical photos of Mr. Cryptosthenes. Look at that handsome Greek man.
All right, Shane's back. God bless.
All right. Excellent. So then, yeah, Shane, whenever you are ready, go ahead and rock and roll.
Yeah, let's let everyone join in. Let's see. I got a lot of information, a lot of visuals. We'll see how we go through here. It's going to be mostly about nautical miles, but also a lot about coordinate systems, Cartesian, spherical, cylindrical, the sky, sphericity, personal dome, spherical trigonometry, and navigating. We got 4.
Now, Shane,
5.
I was told at the end. I was told at the end of this presentation we would have enough knowledge to make our own globes.
Yes, you will. You just need the time, know-how, wherewithal, and the attention.
Very cool. Thank you, brother.
I forgot when I do this, I can't control the audio. That's all right. I think we can just go. Oh, yeah. So we'll start it off with, do I need to have push to talk on for this? Are you going to hear my dog for this? I think you might. I think you might hear my dog. Here's what we're going to do.
What language does he speak?
Irritation. So when I started to look into this, I could only find one video on the fighter side that would like lay down the law, and it was Mitchell from Australia. I had used some of his stuff for some navigation earlier, so I wanted to take a look before I started. But it's a little bit. It's only 4 minutes, so we're gonna take a quick peek at it.
Hello, how are you doing? This is going to be a quick video on the truth of what is a nautical mile, because there's a lot of rubbish out there about them being connected to a globe Earth, which is not true. Nothing to do with a globe Earth whatsoever.
God, this guy's way too Irish.
What is a nautical mile?
I can't tell if he's
1 nautical mile
wrong
equals
or
1 minute of degree. 60 minutes of degree equals 1 degree. So 1 degree equals 60 nautical miles. Degrees are measured with angles, and angles to the celestial objects measure a difference in degrees from a starting point of 90 degrees. For example, an angle that is 36 degrees off the horizon means that there is a deficit of 54 degrees from the 90. So that's 54 degrees of celestial distance from the observer's position, which gives us a straight line sky measurement of 54 degrees by 60 nautical miles, which is 3,240 nautical sky miles. So nautical miles have absolutely nothing to do with the surface of a globe Earth. They are a measurement of the sky, which are then translated onto the Earth's surface via the zeniths of the observer and chosen celestial object. Surface-based measurement is done in statuette miles. Statuette miles are not a reference of or determined by the sky. Only nautical miles are a measurement of and determined by the sky. There is no such thing as a globe-based nautical mile. The word nautical is defined as of or concerning navigation, sailors, or the sea, maritime. The word nautical has no connection whatsoever with heliocentric belief or claims. There is no globe miles. Okay, this is very simple. Okay, here is the GP of the star. Here is the observer. Here is a 40-degree angle, right, to the star, which is here. Okay, this is the observer's zenith here. This is the zenith of the GP of the star. They have a co-altitude. Okay, I'm just going to read this out here. Then I'm going to show a very, very quick demonstration to show exactly what nautical miles are and why there are 60 nautical miles per degree. Okay, 40 degrees of angle. Okay, 40 degrees of angle leaves a deficit from 90 of 50 degrees, which works out as 3,000 navigators minutes, or 3,453.338 statute miles of surface distance. But a more well-known term when referring to navigators minutes is nautical miles, as they had to convert every single navigator's minute into an Earth surface equivalent, and that is why 60 navigators minutes became 60 nautical miles. Attention, 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 this is the important part. Navigators' minutes are sky miles and have absolutely nothing to do with a globe Earth or heliocentrism. Nautical miles reference the sky and statute miles reference the Earth. One is for distance, statute miles, and the other is for navigation, nautical miles, or navigators' minutes. Okay, so this is how it works, right? So see this purple line here? This is the 3,000 navigators minutes, okay, or 3,453 statute miles, right, in a straight line distance. But because it's in the sky, it's not a mile, right? It's not a statute mile. So what they had to do is take all these navigators minutes, right, once they have determined that distance, which is a co-altitude distance, they then take those 3,000 navigators minutes and bring them down to the surface of the Earth and call them nautical miles. That's why there is that is why there is 60 nautical miles per degree, because there are 60.
Right, but poor Mitchell's assuming like, oh, we'll just take it from our flat level sky, put it on our flat level ground, it'll be fine. Stop being crazy, guys. And it's like, oh, no, that's not how it works, though.
Minutes per degree, right? 60 navigators minutes per degree. That is why we have 60 nautical miles per degree, but we have 69 statute miles. Statute miles are surface-based measurement, okay? Whereas nautical miles, or a better term for them, navigators minutes, okay, are a sky-based navigation distance. Two different things, right? Just because they have the word mile behind them, one is statute and one is nautical. Look at the word nautical. What does it mean? It means navigation. It's a navigation mile, right? Nautical miles, navigation miles. Navigators minutes. That's what's going on. So it has nothing to do with a globe, nothing to do with the center of anything or any other idiotic claim. Okay, they're navigators minutes. That's why there are 60 of them per degree, because 60 nautical miles per degree, because there's 60 navigators minutes per degree. Now, I can't make it any more simple than this. Either you get it or you don't get it. Thank you.
And what do you guys think about Mitchell from Australia's video here?
Very informative.
Do you think?
One sky mile.
I wasn't there, but maybe there was some sort of uproar going on where he had to release a video. Everyone was maybe claiming all the sky miles were globe miles without evidence, and he was like, I'm going to shut that shit down or whatever. I think that's the feeling I got.
Oh, yeah. He got into a sextant fight with all the, globularist crowd.
Oh, did he? Okay, see, that makes sense. That's the context. Yeah, but I was like, what?
Yeah, he went hard on the sextant. He had a whole series called like the Year of the Sextant or something. And yeah, they were very upset. There was a lot of back and forth between the globularist and him.
Gotcha. So that's why he was all defensive, right? So I feel like I first found a video of him showing me how to like navigate before I came to Flat Earth, and then the only other video I found was this one from my advanced years going, there's some fuckery going on there, Mitchell, though, buddy. I gotta tell you, there's definitely not straight application of sky to ground. We know we have a celestial sphere. We know we have a geodesic WGS84 and long lat and all the sorts of, conformist infrastructure of sphericity that they're going to adhere to. So we know that that's a real thing. And in fact, we have what's called the geographic grid and geographic coordinates. Like everything that we exist in, it takes place within these longitudinal and latitude skeleton framework, right? Sphericity is a nature of this because of the nature of how they derived it, which is always from the sky. Because we see the sky as a little bit curved and receding, then things rise and set. Then forever things that we take optic measurements from will have that same effect, as we proved with the 69 miles per degree in the logarithmic chart, but we'll go through all of that in detail. Let's start with this one right here. So longitude and latitude, the main culprits for all sorts of sphericity. If you're working with them, don't. If you're doing it, you're in the wrong place, right? Like this is not where we want to be. Literally, it's creating the meridians, which are definitionally to measure sphericity. The meridians are created by longitude, and they create great circles and little circles. And great circles is a big part of how they map or prove, latitudinally and get the globe map going. But of course, by verifying with the sky. Right, so this is not a projection. It's not a map projection. It's not a type of a way to display data. It's a completely separate infrastructure set of data. That's what I've been trying to tell everyone. If it's on a map, right, it's in this coordinate system. If it's in this coordinate system, it cannot be flat correctly, right? It's going to be inherently flawed and have to suffer by the deficit of the map projection options. Each platform or each map type has a deficit where it won't be able to do equal area, equal time, something like that. It'll be good at some things and lose the other thing. But the real data, the real life actual map data that we have is only in longitude and latitudinal form now, unfortunately, right? So this is just the basic longitude. It's the grid system, latitude by the sun is on the equator, 0 to 90, longitude all the way down, all the way through. We know the story of longitude. We know the story that they gave us of longitude, of a nice happy a RAR file dropped in 2014 from our buds at the Royal Society, telling us how the Board of Longitude empowered and elected themselves to give themselves their own longitudinal serving to send people to create a chronometer, to get the actual timepiece, to get the whole thing sorted. So what we take from that, though, is that they needed longitude. They needed longitude. We didn't need longitude. Nobody else needed longitude. Everyone was sailing around fine before that. They needed longitude because the globe requires longitude and latitude. Absolutely. So if you've never heard of this, it's called the graticule. It's actually the globe. It's the only thing we've ever been interacting with is the graticule. We've never even had a globe, turns out, or a geoid, right? We've only had a graticule. So it's the actual gridded network of longitude and latitude. So it's the actual infrastructure of sphericity. That's the graticule. And if we're dealing with it, again, we're in the wrong spot. So if you have a graticule, then you can do these type of projections on these type of grids to have these type of benefits and deficits, right? The one on the plane in the lower left, super easy. It's a nice spherical coordinate from a Cartesian with a cylinder of infinite height. That's a familiar coordinate system that we're used to. You got the cone on the right, you got the cylinder over there. That's just like a Mercator or equal projection. We'll get into a whole bunch about maps too. And then, of course, the globe graticules over there. Here is one of the PDFs that I have. There's about 15 or 18 PDFs that I went through for all this stuff. This one is just showing you a basic globular projection, but it's if you're dealing with trig, you're dealing with longitude and latitude essentially. So they're just going to reify the globe and offset anything that that they miss with sphericity. That's essentially what this is doing. The unifying factors here. Actually, let's do this one first. I love my lads who are like, hey, how does this flight path? How come it doesn't make sense on this map? And it's like, whoa! Stop comparing globe to globe to glob to globe. It doesn't make any sense. Only the globe wins. It's always the same data projected differently. We have a visual scaling per map. And if it has longitude and latitude, and it does, then it's able to be projected into any receiver or any projection, any one of these conical, basic forms that people make up for whatever purposes. If it's not longitude and latitude, it doesn't have that, then it can't be projected. So essentially, if it's on a map, It has longitude and latitude based on the sky, based on the celestial sphere. Now, it's 100% a fact that the celestial sphere has been mapped point to point to globe Earth. So literally, they mapped it to the globe. It is the globe. The celestial sphere is the globe effectively. But look, the Gleason's, but the flight path over here looks like it's way longer. And it's like, no, it's the same distance. It's always the same distance. Every map shows the same distance. It's just a visual scale. The fact that so many people have been trying to argue about the distance on Gleason's is mind-blowing to me still. Just because we know for sure that one is the equal everything, equal latitude, equal longitude. Not to mention that it specifically takes the longitude that's a geodesic and makes it a linear measurement of distance, which is magnificent. Again, stop comparing globe. What do you got over there? Same thing as I got? Mine's bigger or whatever? Is equal area, is conic projection, is Mercator, is globe, is orthographic, is Gleason. All the same data. No difference between them. So this is just a little mean saying if you input something into a geodesic WGS coordinate system, you get output in the WGS coordinate system. Oh. So another thing is about the graticule, the properties that it leaves you with, some things you have to handle. You have different ways of creating great circles. So one of the major functions of longitude is that it's the creator of a great circle. A great circle is a marker of how you can find a baseline for a coordinate. So longitude, essentially, right? Remember when they had to do the prime meridian at the observatory for the Royal Society 300 years before because reasons? Yeah, well, that's what they wanted. But before that, right, you could use things like the Equinox. The Equinox was a well-known event where everyone would set their time to be able to mark longitude. Right? From that point on, when you knew what the last equinox was, you knew you were set with longitude. Right? There was no need. So now that they have prime meridian, everything's scaled and unified to their time, but it's only good for them. So as a great circle, it has to be on the exact equator or on the prime meridian. It's every other circle is a little circle. The great circle is the point of the biggest on the sphere, right? So in the theoretical world of sphericity with longitude and latitude that converge, then there are two one great circle on the equator, one great line, one great parallel on the longitude for the prime meridian. All the other circles should be smaller.
I think the synonym there is longest possible circumference.
Yep. Oh, definitely feel free to chime in. I don't really have much set for this. Is all free balling over here. Yeah, longest arc. That would definitely be a good way to put it. And now, let's get with the definition of the nautical mile. So, I mean, Mitchell was he was right when he defined it, and he was not right when he inferred what it would mean. Because when I looked at it, it was very much sphericity, and every time I went, it was assuring me that it was requiring sphericity, and absolutely positive that it was dependent on sphericity. It's like, oh, okay, so this is where it gets a little bit rough. So it says, you know that it's real whenever they preface it with the word historically, and they say that every time. Historically, the nautical mile was. Historically, it was. Makes me think that they're lying, but it was defined as the meridian arc length corresponding to 1 minute of degree of latitude at the equator. So what that actually means is 1 minute of travel on the equator, on the biggest great meridian. So that's what a nautical mile is supposed to be. Before the concept of units and miles, it was just an increment. Like a nautical mile was an increment. Like a degree is an increment. A radian is an increment. It's like a percentage. It doesn't matter what it is. You can count and sort of notate the same. You can do 20 minutes, 20 degrees, 20 Shane degrees, 20 stone degrees. It doesn't matter. It's all degrees. It's all just based on the circumference of a circle. Right? And that's the important part, is all of that is based on just the circumference, nothing else of the circle. And the circle has a circumference as well as a sphere. Right? They do that quite a lot. They attribute to sphericity what they could to a circle instead. So it says, again, historically, the meridian arc length of 160, 1 degree, about 60 minutes, 360 degrees equals, 21,600 nautical miles, which would be the actual circumference, 21,600, right? So they defined it by getting the actual circumference of the Earth and then doing the spherical formula for an arc length to tell you that that's the actual definition. Now, Mitchell says that this isn't to do with sphericity, but I mean, if it wasn't for me, where it wasn't for the optics presentation where we had to use a circle to derive the arc length, to use that to get the distance to the horizon and all that, I'd have been like, well, right here, I'm telling you this is sphericity, but I'll just keep going. So again, I did a couple of these because every which way you look, it always tells you, well, first of all, with a preface, and then also with a shaking grin. Yeah, definitely because of the spherical nature of the Earth, we can do this arc length, and that's why we get a nautical mile. A nautical mile is because of sphericity. There's so much that I had to go back so far to find anyone who would identify it or define it without sphericity. But of course, an arc length is just from a circle. So I'm not sure why everyone was concerned that it was a
good explanation of
oh, we can't even hear me, huh?
is versus a chord.
No, we can hear it. Just got to turn it up a little bit.
So
1 second.
That's super low.
this is our circle, and as we go along, you can see that the arc length, which represents this curve right here,
I think I'm just gonna talk over it anyway.
something like
Okay.
this straight line.
It's just telling you that it's an arc length, so it's doing the point line distance between a curve distance. That's what it's comparing this line to the curve line. That's all it's doing. When you get the chord, chord and the arc length.
Yeah, yep.
Whatever increment that's in, and as we can see, if we go,
You can get an arc length for all the way up till I think like, yeah.
and again, another one for chord length simulation. All we can do.
Yeah, I was all over GeoGebra for a couple of days. Ruhif would be proud.
Is moving, that means the angle is
You showed everything except that at 180, that was pi radians.
Yeah. Yep. Yep. A lot of them I do the whole 360 for it. And now my favorite one for what is an arc length, because he said that the nautical distance would be, what do you say, the sky miles and not statute miles. But that's not the relationship that I see. The proportionate relationship is of arc to chord that I can see, or that of curved geodesic to linear version. Because what we have with the globe radius is exactly the same thing. It's if it's 69 miles per degree linearly, right? Then times how many degrees of latitude? 9 degrees of latitude, 90 between the equator and the North Pole. So 90 times 69 is 6,210, right? So it's not 3959. It has to be 6210 because that's the geodesic long length version of, that's the arc length for the chord of the radius, right? The radius has to be straight geometrically. And that straightened out, when that curve straightened out is the radius. So I'm not sure if that globers know that, or if they do, they're not wielding it correctly. Like that's just a fact of geometry. And the good thing about the Gleason's map, right, and that specific projection is that it nullifies all great arcs, all meridians, all geodesic arcs become linear lines. It's wonderful. Right, so does it require sphericity, this arc length? No, just that you have a circle. And we do live in a circle, so I'm still fine. Also, when you're actually looking at the world, you have a spherical limit. So the circle could very well describe a top-down view of the limit of your vision, right? Super easy. This is just an arc length circle next to a bigger sphere from a complicated Cartesian spherical coordinate system later, but I just used this one because it has the circle inside to show you that inside the sphere is this arc right here, just laid out, doing the same thing. No big deal. Oh, I said that. Gotcha. All right, plane in the middle functions exactly the same, and here we go. Oh, look, that's what they're using, though, is a sphere with a plane right in the middle to say this plane along this arc length on this meridian at the equator is a nautical mile. So they're very sure. They're very sure about that. I've looked up so many times that this is the only way I've ever seen it defined. But for us, it's not the Earth spinning, right? It's the stars spinning, or it's the sidereal motion of the sky that passes overhead with no effort. So it's a little bit weird for us to say that, well, a nautical mile should be the amount of ground the sky covers when I do nothing. Wouldn't that be equivalent? Anyway. Right, so I think when I asked a couple flat earthers before, like, oh, the nautical mile, is it, like, yeah, I think it's from the curve. They're like, no, it's fine. It all works. It's great. Like, nobody cares. Everything's cool. Nautical miles work. Sky miles are fine. The celestial sphere isn't a problem for us. And it's like, well, I disagree. It's a huge problem, and people know about it, right? Like, they've been telling us about this for a long time, as Witsit pointed out on the last stream. And if you've read Morals and Dogma, or if you're familiar with the square and compass, then you know that's what those things are for, right? You got the square and the compass. The longitude, linear line wielding straight edge, and then you have the curved, perfect sphericity making curved infinite circles compass, right? Of course, you put them together, you get a squared circle, which is kind of cool. I'm going to read a bit from Morals and Dogma here, which of course mentions the square and the compass, their main symbol. It says the square is an instrument adapted for plane surfaces only, and therefore appropriate to geometry or measurement of the earth, which appears to be and was by the ancients supposed to be a plane. The compass is an instrument that has relation to spheres and spherical surfaces and is adapted to spherical trigonometry, or that branch of mathematics which deals with the heavens and the orbits of the planetary bodies. Now, it's almost weird because that's almost exactly the inverse of what we get taught in school and through the mainstream. Almost like you want to invert everything the Freemasons tell us, right? So if they're, through the control of the World Society and the control of the educational system and academia and our schooling, if our education taught us that Earth is spherical and our vision is planar, and we know you see linearly and infinitely, then of course we should assume the opposite. We should assume that we see in spherical geometry and that the Earth is planar and in planar geometry, and the sky is spherical. So just invert everything that they said. They told us the sky was linear. We can scale it to infinite distances, to just like our vision is linear. And they taught us that the Earth is spherical, right? So invert all of that. We get a planar Earth with spherical vision and a spherical sky. And those are the geometries that we should be working with.
Totally. That's actually what I was thinking of pointing out about 10 minutes ago when you were talking about latitude and longitude to begin with. It seemed, and projection, that it seems that entire device was just a product of Euclidean / Cartesian zealots trying to deal with curved visual space as a problem.
Very smart, very astute observation. So that's exactly what it is. The whole thing actually is them contriving the limit of our vision and the slight curvature of the limits of our space for there being this physical nonsense thing that no one's ever seen, that can't exist, and everything's been built around that.
We'll deflect the vertical and adjust as we please.
Forgot about this is the A crew. We already know about that. This is, again, the square. It's formed by right lines. It's adapted only to a plane, belongs only to geometry and to earth measurement and that trigonometry, which deals with planes and with the earth and with the ancient supposed to be a plane. That's a quote from Morals and Dogma from our boy Albert Pike. And then again, this is the same thing, a different way to put it. I think I found a better image of it for the square and compass. I mean, I've never used one of these, but if you have to draw a circle on a map and you have to do a straight edge and you have to actually look at the specific layout of the equidistant grid line that you're working with for your life, then yeah, you need a tool like this for sure. All right, so there they are again. I think I inverted them. Yeah. Man, the compass though, the sphere within spheres has gotten me. What's the wheels within wheels, or the higher within higher? This particular one is, supposed to be Cartesian coordinates, and then of the radius creates a plane within its own area every which way it can. But we'll definitely get to that. A whole bunch of personal spheres along the equatorial belt there, mostly just for fun, because it's all for the compass. So, does the meridian arc require sphericity? Because that is definitionally how they brought in nautical miles. And you bet your ass that is literally definitionally requires sphericity, requires longitude, latitude, actually, specifically, to even be possible. The function of longitude, besides providing a nifty timepiece for the awesome chronometer that I'm sure really existed and that the dude really made, was to provide the offset for the coordinate for the infrastructure for globularity, without which everyone else would be fine and they would not have the globe. But the meridian arc is very specifically to prove the measure and, I think, width of the Earth. And if you look through the history, or if you look through Wikipedia and the internet, you'll find a lot of people talking, experimenting with, notating about, researching, analyzing, or just otherwise speaking of people who were doing meridian arcs, who took a meridian arc, who compared a meridian arc, who sailed the meridian arc, who it's a lot. It's pretty popular. It's how they used to be able to just sail. They used to, pretty much dead reckon and go east one bearing and go all the way around the world, right? Do a circle route. So they know that they could hold a bearing by turning constantly, right? By doing a circle essentially. And they knew that they could do that all the way through, and that would be the longest circle arc that exists. They also knew that it out to the equator, at least, it got bigger and bigger and bigger. Each arc was a little bit bigger. And they accounted for that in the definition of the nautical mile. So it says, in geodesy and navigation, a meridian arc is a curve between 2 points on Earth's surface that has the same longitude. So in the definition, it's on a spherical Earth with longitude. So I would say that is definitely requiring sphericity. And it may either be a segment or its length. And the purpose of measuring is to figure out the shape of Earth. Oh, right. One or more measurements could be used to infer the shape of the ellipsoid that best approximates the geoid. So again, we're mixing that geoid with the ellipsoid. We're doing deflection of the vertical, geodesic surveying, and at the end, a wonderful bout of astrogeodetics, which is, of course, amalgamizing the astro and the geoid. So it says the earliest determinations of the size of the spherical Earth required a single arc. An accurate survey began in the 19th century. Oh, the 19th century is when they had the best measurements for the fake globe. That's weird. And it says the latest determinations used astrogeodetic measurements, of course. So for the meridian arc, we have one, right? We have the prime meridian. And then from that come the nautical mile and the meter. We also looked up the meter. The meter definitionally is based on something else, the speed of light, I think, but that's crazy. It was decided at the same conference. Let's see. So yeah, this is dealing all with the circumference. So we're back to 40,000 kilometers or 24,000 miles, and exactly equaling 1 minute of 1 degree, 1852 kilometers. That's what they equate a nautical mile to. If you just use that value, then you're fine. You'll never notice anything wrong. That works. That's real. But if you think about what that is and where it comes from, then you have issues. So we have great circles and we have every other circle, which is small circles. They're all useful. They all do a certain task. There's a whole bunch of celestial navigation on here with some alt-as and some right ascension and declination, but we're just going to buzz through that because it's not really necessary to what we're trying to show you. If you want, we can go through all that. It's a really technical way to do it, but the main point I'll point out when we get there. This one is still based on the circumference, right? So they always do. I mean, you can do 2 pi r for the circumference, the radius, right? And that'll get you there. That's super easy. But they get that start from backwards. Then they do it in kilometers. They do whatever the total is divided by 360, and that will give you the slices of meridian, right? So by definition, it divides into 2 hemispheres. So literally has to be a sphere. Equator and prime meridian are it, and that is all. It says the travel along the great circle is the shortest distance between 2 points on a sphere. The principle is the critically important in the air and the sea, where following a great circle minimizes travel fuel. And I mean, I don't know if that was the case. I think that was the only direction they could just bear without any markers. Like if you can't see the land and there's no stars and you're cloudy, you can just bear east. You can keep bearing fucking east until you go around in a circle. I think that's what they meant. So all of longitude and latitude is inherently based on sphericity. It's all spheroidal. It's actually the infrastructure for the spheroid, right? Latitude and longitude are based on the concept of great circles. They do use spherical trigonometry, but not for CellNav itself, for the conversion of CellNav from the right ascension declination into the geographic longitude latitude. That is spherical geometry. We'll get to that in a bit, but that's also where the astronomical triangle comes from, and funny enough, where they manufactured spherical excess out of the sky. So for the mapping, they use latitude and longitude, which they could do account, quote, Earth's curvature, but really, which are based on optics and account into the descent of our vision. Someone want to pop in? No. So a great circle versus a little circle, right? Dividing it, if it doesn't divide it in half equally, it's not a great circle. That's all that means. And we're going to look at a quick video of my dude here.
Of the geographic poles and equator onto the celestial sphere, so it can be thought of as a celestial equivalent of terrestrial latitude and longitude. The equatorial system is equator-centric, meaning its angular coordinates are measured relative to the celestial equator. Unlike the horizontal system, the projection and layout of the equatorial system in your local sky is based on your geographic location. The embodiment of the vertical angle in the equatorial system is declination, abbreviated as dec, which is comparable to geographic latitude. The horizontal angle in the equatorial system is either right ascension or local hour angle, abbreviated RA and hour angle respectively, which are similar in function to geographic longitude. I'm guessing that the majority of viewers live in the northern hemisphere, so we are going to be focusing on the system as it relates to the North Celestial Pole. To make things a little easier, I'm going to be using the abbreviations for the northern and southern celestial poles, which is NCP and SCP. You can imagine the coordinates of the equatorial and horizontal systems as being similar in function. Declination measures apparent angular offset from the equator, just like altitude measures relative to the horizon, and both create minor circles on the celestial sphere, aside from their origin points, which are major circles.
So we're looking at the blueprint for how to map point for point the celestial sphere to the Earth, in case we're missing that.
Azimuth and right ascension or local hour angle are of the geographic poles and equations are perpendicular to the equator and intersect both poles, while azimuth is perpendicular to the horizon and intersects the zenith and nadir. Basically, the coordinates of both systems are identical in function, except in the equatorial system the poles function like the zenith and nadir, and the equator functions as the horizon. The first and most important concepts we need to address are the celestial poles and equator. These can be imagined as projections from the Earth onto the celestial sphere. The celestial equator is a projection of the Earth's equator, creating a major circle on the celestial sphere and dividing it into two hemispheres, north and south, with the poles located at 90-degree angles relative to the equator. The celestial poles would be lines extending from 90 degrees north and south latitudes, creating points at opposite ends of the sphere. Since these celestial points are based on the Earth, they do not change very often over time. We're going to talk a little bit more about precession and epochs later on. The next step is to determine where these celestial markers would be projected in your local sky based on compensation for your terrestrial location. Let's take another look at our example sphere and suppose that we are located at a latitude of 0, which would be any position on Earth located along the equator. Since we are located on the terrestrial equator, the celestial equator will overlap the prime vertical at a 90-degree angle relative to the horizon.
And that's how you get all the measurements from that base right there, that intersection. That right there is how you get the time base, the required missing component to get every celestial object's location on Earth.
We're no longer getting the
east and
visual
west
on
along
that.
Oh. Was that napalm? It's not napalm.
Yeah, what's up, man? You're telling me that they're mapping the celestial sphere to the ground, Shane. Come on.
They're like, they're not even doing that. They're getting us to do it and then tell our kids about it and then not know what it means.
Yeah, brilliant. Is that the stream finished, or are you going to do more?
We haven't even really started.
Lots more to go.
I was really enjoying it. I was like, why did you stop?
No, I didn't even know that I stopped, I guess. I have 3 screens and my neck was craned this way. I didn't see it stop.
We just at one point towards the end there lost the visual from the video that you were playing, and it was just showing your black background.
Your zodiacal background.
You good now?
You're not even streaming.
Oh,
you're not up yet.
I'm only in Canva.
You're in Canva.
I'm sharing Canva to myself. Yeah.
Yeah, well, that kind of sucks. There we are. There we are.
All right.
All right. Don't know what happened.
Relative to latitudes above or below the equator. Basically, for a given latitude, the entire equatorial system rotates based on the latitude's angular separation from the terrestrial equator.
He put that so nicely. At first I heard that, I'm like, what the fuck? That is what it is, though. That's going to be in radiant angle to it. Okay. To put it like that means I'm going to be using that as an offset to calculate everything I need.
Meaning that the poles have an altitude either equal to or opposite of the given latitude.
Right there.
A northern latitude causes the apparent position of the NCP to move upwards in altitude relative to the local horizon at an angle equal to the latitude's angular separation from the equator, while the SCP moves below the horizon at an equal but opposite angle. This also means that the apparent position of the celestial equator will also tilt relative to the prime vertical at the same angular offset as the poles. The apparent rotation of the poles corresponds to the rotation of the entire coordinate system at an angle of the same magnitude and direction as the poles.
Funny that we have to look at the same observations and they make up some backwards compatible heliocentric lore that explains the same thing that we see, and just like, oh look, the stars circle, and they circled again. And you're like, no, you know what happened? Anyway.
You know what happened? We moved and rotated.
Backwards faster than the speed of sound, broke some barriers, rocketing around the universe, spinning, wobulating all sorts of axes. That's what happened.
And we did it a billion times in a row, and everything up there looks exactly the same.
Yeah.
What I want to know, though, is if my car is going 1 billion miles an hour through the galaxy, why have I never been given a speeding ticket?
That's a very good
I
question.
didn't see the sign, officer.
So this is saying true direction or an azimuthal is one of the facets of an azimuthal equidistant projection. But what it does for these great circles that we just talked about is it nullifies them, completely straightens them bitches out. Remember, that arc chord relationship would be gone, that 6210 becomes 3959. And so the shortest route is still going to be the spherical equivalent, but it's for us just a straight line. So back when you have your graticule and you're projecting it onto your spherical infrastructure, then you can choose which type of projection you want to put your data on. Again, if it's not in the longitude and latitude format, if it's not already in this infrastructure of sphericity, you can't do this. Here you go, ordinated. Yeah. Then you can't put it in any map. It can't have data. You can't transfer it. You can't translate it. Can't do a coordinate transform. Can't do anything. Not allowed. Can't be done. So when it's in a map, it's already part of this data set. And the data set is the celestial sphere pushed onto a fictitious globe curved Earth. So the coordinate system is a sphere, right? They did math for the sphere. They did descension rate for the sphere. They do trig for the sphere. They do everything for the sphere except for the orbit, which they made ellipses, of course. So we have the equal area, which is just meaning that you're preserving the area around each point. The conformal orthomorphic, which is just local angles and shapes. And then you have equidistant projections. That's the most common, I think, types of like azimuthal or cylindrical. And then you have compromised projections where they're a little bit of both mix and match. Right, so we're all familiar with these, or if you're not, I am. I've been looking at these a bunch over the past couple months, pumping out like goofy looking maps like this to show globers that it's all the same, but they don't. All they care about is the flat one. They go, oh my God, look at this map. It looks so crazy. And it's like, yeah, but this is the same as all the other ones. And that one's in a fucking M. No? All right. Back to the nautical mile, where we have a complication called the knot. We have a knot in a nautical mile. So if we have one based on distance and degrees and a circle, then of course nautical mile would be a derivative of that, I would think. For distances north or south on meridian or longitude, and for distances east or west, it becomes that formula. And it's just 1 minute, which is 1/60th of a degree all the way through. Can we get longitude on our flattened out geodesic linear map, do you think? Oh wait, is that the back of the map where you put a paddle and a arm and instructions on how to actually mimic it to lower it to denote longitude and still get the geodesic arc? So I mean, we're still going to get a globe distance, but we're going to get a distance that's going to be pretty accurate if we just follow Gleason's remarks over here. So if we add up all the degrees and we take a look at the longitude lines, because again, if it has longitude and latitude, it can be endlessly and losslessly translated, conformed back and forth between all the available map projections with no loss of data. I wonder how we use it though. Oh, wait. On the back of the map for Gleason is, if you took it, is what it says right here. It says that the latitude and longitude correspond and that are indicated by the circular, let's see, the circular lines, and he has the arms, he calls them, the arms J and the arms O, put them into a socket. So essentially he bought a ruler, where he patented it with this 2 rulers that on the ruler it just has 10 through 90. 10 degrees through 90 degrees of latitude. You line it up with latitude and then it denotes longitude. And you swing that bad boy around. You figure out what time it is, and you line it up with the Greenwich Mean Time, and then you get your longitude component to get your offset to get your component. So that's how you would be able to tell on any Gleason's map, or any map that has longitude, really. You'd be able to tell where you are and what, how far you are from any other point. Not even just from the north, but from any other point, because you're just using longitude and latitude. So let's see here. Here's an example of New York, and he has the 15th meridian, which is 15th parallel line of longitude, and he has the arm H, and he puts it over there for an example, and it's 0 hours and round numbers, and then he says, look at your own pocket clock, and then you do an offset. So it's relative to the position, you have to add the time, and then the time stands already computed, he says, to any child who is able to read the time of day from the face of an ordinary clock. So that's a tough one for the people who are like, there's no distance scale on that. And you're like, oh, well, it's the same distance, but there definitely is one. And again, it says on the back of the map, in order to procure the corresponding time of day or night, any part of the world, you must find the meridian, your timepiece, and then next place the index arm on that meridian, the other one where you desire the corresponding time, and have the difference between the two. There you go. So point blank, highlighted, and black and white. What is this one? Oh, so yeah, the altitude of the sun. Of course, the Gleason's map is a sun map, really. It's based on the sun, based on latitude, based on the equinox, based on that latitude. Because of the equinox, you can get the longitude, and if you're already getting latitude from Polaris or other stars, then you have your own coordinate system without any unified longitude and latitude anything, and you should be fine based on the sun. So he used the sun in the Gleason's map for sure. He divides it up between 4 quarters and does a little bit of explaining on how that would work too. And of course, we have this ruler at the bottom. There's a visual distance scale. So it sure is goofy, right? To look at a long arc on the outer edge of the map, but then to do the longitude math and then to apply the Tesseract's, warp factor to be like, oh, well, that's visually not scaling it correctly, and it's all the same distance. Like, oh, yeah, it makes sense now. So there's no way you're going to get a different distance using the same longitude and latitude. That's what keeps everything equal area and separate and exactly incremented, so you'll never be able to deviate. But if we go back to the nautical mile and we think about the other possible definitions, or what they would have interpreted it as before there was a predisposed sphere that everyone was talking about all the time and forcing on you, you'd probably just think about the actual circle, because it's 360 degrees in a circle, and then arc, and then regular measurements, and there would be no need to go any further than that. You could just be like, well, we live in a circle, and you divide that circle up, then 60 nautical miles per degree would equal the same globe circumference of the flattened out circle. Of course, we know that that's not the right number, because 6210 is the flattened out linear geodesic equivalent. But we can still say that if we look around for just say what we have for longitude and 15 degrees, so it's 60 nautical miles per degree, so we have 900 nautical miles in this 15 degree section, and then we have 24 of those, say, around, so we have 24 sections of 900 nautical miles based on longitude and just the circumference of a circle. Then yeah, we would still get right back up to the exact globe circumference of, whatever the nautical mile equivalent was. I think it was 21,000. So if you take a look at that, this equivalent section, there you go, 24 sections all the way around, and then we get that, 24,600. So, I mean, that's one way to do it. This tricky thing they do with spheres and circles is they try to confuse you and apply things to one or the other, but many things that they apply to also a circle. So something to think about. So this one would make way more sense if it's just 1 minute of a degree of a round of a circle of a clock, or even better, would be around what your visible radius would be. So it says, if you're smart, right, you can do what they do, and you can take an observation of one nautical minute. You could technically observe 1 nautical minute and know that, you've seen a day before, you've seen nighttime. You know that there's a sun that goes back around and will come back around over a certain amount of time, and that when it comes back, you'll know that, oh, well, then that's the mark in the end of this cycle, and you can calculate a percentage of that cycle since then. That's all a nautical mile or degree would be, right? That's a unit increment of a celestial period, right? Really? So it says 1 minute per nautical mile, but it's really just 1 minute of, let's call it 1 unit, 1 incremented unit of sky time or sky distance, I guess we could call it, because time would be distance up there. So it says you can deduce the circumference if you just know that there's 360 degrees, and you can do backwards 60, 360 times 60 equals 21, 30, 60, and then you can do it backwards. So you can be like, from 1 nautical mile at 60, if I know that it's exactly 1852 meters for a nautical mile, then I can take that increment, go around the clock, and figure out exactly how big the quote circumference of this thing is. So we got to go quickly into the coordinate systems that they're based on, because we're living in a geodesic coordinate system that's a geographic one of longitude and latitude that has enslaved all of the world, and people on their phone don't even know it. So that to the point where they have, I don't know if the Earth's a sphere, but I'm going to check Google Earth on the distance, and it turns out it checks out fine. Like, oh, no way. But essentially, we're not going to deviate too much. But the coordinate system itself is not, a thing to harp on. It is just a mathematical tool. The only thing that makes it bad or good or applicable is a datum. And the datum would be something like a WGS84 or the ellipsoid model, the clock geoid, the 700 of them. They've made them all the time. But the coordinates from this system can be transferred to another, and then you go through, our favorite thing is going to be coordinate transforms. The 2 basic systems that, actually, I should read this one on the left. The great circles are what causes a coordinate system, right? That is the basis of all alignment, the zero marker, essentially the home. Like this, you can't have a cycle without a start and an end, and that's what marks the start and the end, is the great big circles. So you have the horizon, the celestial equator, and the ecliptic. Those are denotable visual markers that you can set your longitude/latitude by. Right, you'll know the markings of the world by looking up in the sky. Go figure. But the two coordinate systems that we don't deal with is the geodesic coordinate, and then you have the geocentric coordinate system. I mean, that's just a celestial sphere. It's for essentially a horizontal alt-az thing, like stellarium. If you have just an azimuth, which is an angle from a set direction or 0, then you can do an azimuth, which will give you an angle around the circle to give you a direction, a point, and then a height or an altitude. So we're not going to use any one of those, but we're going to go a little bit simpler and use our celestial, let's call it the local celestial sphere, where everything's the same as the globe as they marked it and mapped it, except it's not retarded, makes perfect sense, and backs up by every ancient civilization, every map, and all the cave drawings. So we're not off on our own NASA land, so that's comforting. But if we try to just envision it like this again, right? If we're just sitting on our flat Earth with our little sky dome that's half of the Earth, and the sky is just spinning above us, doing its thing, and we say, hey, how much of that is 1 nautical mile? It kind of puts a different connotation on it when the Earth isn't spinning and you're not moving with it, but it's essentially just going to the zodiac, right? And we'll get into that later. There's a reason I keep putting the zodiac here. It's because the ancients celestially navigated by using this wheel, right? They just chalked it up to 30-degree increments of close enough, and then they just used that essentially. So these are still coordinate systems based on the stars. We have cylindrical. Cartesian is not based on the stars. That is the only one that is legit math and can be used to do bad, but is itself inherently harmless. You have the elliptic, the cylindrical, parabolic, cylindrical, conical, prolate, oblate. We're going to be focusing on spherical and Cartesian because, of course, spherical is our geocentric, natural, walking about world. Oh, we get some music. So this is coordinates for spheres and the polar coordinates. And
each sunset framed by calculus, horizon curves a parabolic fuss. Math weaves
it shows everything all at once. All right.
And this is how the same thing would work on the sphere. We would do this. It would go do, do, do. It goes out first on the Cartesian, then it goes up based on the optical angle.
The reason that we're showing this right here is because we're going to be living in here. Like, we live in this coordinate system all the time, everywhere. And that what they do is they don't endlessly convert, back and forth, to and fro, distance, linear. What they do is they just endlessly calculate it all the time based on angles of the stars continuously. So it's always going to be their version of wrong, or always going to come up sphere.
So right there, it went through. It did. This is the azimuth. It did right over here, azimuth.
It's comparing right now polar and
this would be the radius. So this
spherical.
actually is at the same point for all of the equidistant points all around it, right? That's what we're saying.
What we're going to do is map out like our celestial sphere. And what this radius here is this is where at this point we create other disks around it that will be the limit of our view. So at every point R, you're going to create a disk like that. That's the math that we'll do. It's going to be crazy to think about, but it exactly is how we see the sky. And it makes perfect. It was so exciting to be like, oh, so we don't live on a celestial sphere. We live on a plane, and all of this gets calculated directly. Oh, all right. So we exist in 3 coordinate systems at once. They're not converting it. We're simultaneously in spherical, Cartesian, equirectangular, and cylindrical. I'm like, well, that's a different way to go about it. I thought they'd have to convert it. Like, is that a geodesic? Is that a curved? Or is that a line? That doesn't matter. We're just going right back to the stars. We're taking our observation angles. We're doing some trig. We're getting right back to that base sphericity. But this is just going over the spherical coordinate system, and essentially it's polar, azimuthal, and distance. So the main thing is that we have a triplet of coordinates that will be able to be projected, spherically, polar, and cylindrically. So essentially, it's always it's in every single coordinate system at once. Not like a map transform, like a mathematical equidistant sort of. It's like geocentric and heliocentric, right? You can at any time switch between the two for anything in the sky with no problem. That's what I made sure of. They're equal, right? So it's the radial distance or the radial coordinate. That is the azimuth. Polar angle or co-altitude, which is they call also the zenith angle. That's inclination. So that's the opposite from the fixed zenith. And then you have the regular azimuth angle and what's the big one? Radius, inclination, and azimuth. Yeah, so the inclination would be this.
1 point for the globies out there watching, all the guys arguing about what happens relative to the horizontal. Look at the top right chart that theta is measured against the vertical. Up from your cursor on the top right.
Right?
Yeah, in that chart, top right. Theta coming off Z is measured. The R itself is measured off the vertical. Not the horizontal.
Very good point.
I mean, in this particular coordinate transform, yep.
Method.
Oh boy, there's lots of volume in here. So what I'm going to do is change that. Canva minimum. Nope. Hey, that's better.
That reeks of AI.
No, I sang it myself, dude. I just wanted truth background music. Yeah, so like I was concerned about the math, and then I realized, oh, there's a GeoGebra tool where I could visually demonstrate it. And what it does is create this disk sphere at every point R. So as it reaches anywhere, everywhere, it creates another disk that we're going to go over. That is just a spherical coordinate system disk of just your. It's pretty much going to put you at the center, put a radius R, let's call it 39, 59 for whatever reason, and extends that outward into a sphere of a circle, and that's you. You're a little circle, and you walk around with a visual radius of 39, 59. It's like, oh, where have you seen that before? It's mathematically perfect if they do it like this. They simultaneously have that existing in every coordinate system so that there's no translation. It's just equal. mind-boggling. Turns out the spherical polar one is the tricky one because polar is like a radial, sort of an analog to one of the other coordinates, where it just keeps the radial distance and projects it outward in the same fashion. So right there's spherical, and I think I'm going to switch to Cartesian. Yeah, right there, regular Cartesian. So this is a nice little output. It shows the equivalence of both. Right now we exist in two frames. We exist as a Cartesian point in that web and that cylinder, and also in our own little sphere at the same time. Right. So the spherical one I recognize more than anything because it's just an angle from azimuth and an elevation essentially. Back to Cartesian. It's not like we're gonna have to do these back and forth, but it's good to visualize what I think is happening. It was necessary.
90 degrees. Next, we will create a series of 16
Oh boy.
cones split evenly up and down the z-axis, with the horizon serving as the plane of symmetry.
We're gonna do little circles real quick.
Each cone will originate from the center of the sphere and have
Oh wait, no, not little circles. We're gonna explain what we just looked at, which would be that cone coming out from the spherical polar coordinate system, which will show you how that gets kind of uniformly wielded across the axes and kind of exists everywhere.
side lengths equal to the radius of the sphere. For positive altitudes, each cone above the horizon will have an increasing exterior angle based on a 10-degree increment from the previous, meaning that the angle subtended between the horizon and the edge of the first blue cone will be 10 degrees. The second blue cone will have an exterior angle of 20 degrees. The third will have 30 degrees, etc., with a maximum value of 90 degrees at the zenith. For negative altitudes, each cone below the horizon will have a decreasing exterior angle based on a 10-degree increment from the previous, meaning that the angle subtended between the horizon and the edge of the first red cone will be negative 10 degrees. The second red cone will have an exterior angle of negative 20 degrees. The third will have an angle of negative 30 degrees, etc., with a minimum value of negative 90 degrees at the nadir.
So a conical projection upward.
The angle between the horizon and the edge of a cone is equal to a given altitude. The complementary angle to altitude is referred to as the zenith angle or the co-altitude, which is equal to 90 degrees minus the given altitude, and is represented by the interior angle of a given cone, between the edge of the cone and the z-axis. From an axonometric perspective, we can see that the outer edges of the cones create minor circles on the surface of the celestial sphere. These cones represent the altitude coordinate, with the cones above the horizon representing positive altitudes and the cones below the horizon representing negative altitudes.
So with that right there is a one-for-one way to transform or convert everything in the sky to what's happening on the ground. Or in other words, a point-for-point conversion of celestial sphere point to geodal spheroid Earth point. Right? And each one of these is a point. And each one of these you could translate, transform, and otherwise relate to the celestial sphere. So why is Earth curved?
Because, now that we have covered
because we see the sky curved and everyone thinks that made the world curved, so they acted as such. Like literally all the stuff they did, geoid, conformity, WGS surveying, astrogeodetics, they're just like, well, it must be a sphere because the sky is telling us that. Assuming that there's people that aren't, fooling us, but actually
coordinates in the horizontal system. Let's take a look at.
Right, we did that. Oh, is this me? Yeah. Right. Man, thank God for GeoGebra, man. You can see how this exists at every point along this circle. So you're creating a disk at the end of your extended radius that puts it projects all of your celestial sky at that radius, at that height. The other aspect of a cylindrical projection like this of equal height is that it kind of breaks height and that they're all at the same height. Almost exactly like how the stars are in real life, how we treat them, how they work for celestial navigation, how we see them, and how they've been for all of the ancients. So we went to spherical and polar before. I said that spherical is the polar analog because they're both radial. And we divide the 3D space into the set of spheres. So we can represent all of that again in all three at once. That's kind of the crux of it, right? We don't need to bother with either one. We can exist. I'm gonna call it Cartesian simultaneity. How's that? We're going to exist in the Cartesian, cylindrical, and spherical coordinate system. It just breaks down to one variable. They have a triplet coordinate point input, and they just change the radius, and everything else gets projected. We don't really need to go over that, but this would be how it works, right? We have the one disk on the bottom, and then another volumisk projected upward with the same sort of radial interaction, and then we have this point as an order triple, which is the height, and then again from the XY plane. So it's embedded geometry that maybe people didn't take, but was super fun to look through to get the background to understand what the heck we were doing here. So we have another point here, and this is the cylindrical version of the same. This is exactly how we're going to work. It's the polar representation of a point in the XY plane. That's all that is. And then lastly, the one that we started with, the one that we see all the time, spherical coordinates or polar representation. And what they have it as a set of concentric spheres at the origin. So what that does again is create a platform, a disk at each point radially outward, and that's how the sky gets projected. So it's just the, like I said, triplet XYZ, and then A is identified by P. So we have P is the radius vector, and that's the distance that we have, and then we have the angle between the X and the projection and on the XY plane, and then we have our theta. So that's pretty much it. Boy, that got super loud. So yeah, the one for him, and then one I get to play with it. So again, XY, but we have that one coordinate Z, which we're gonna play with. The altitude right there. I didn't quite get that at first. I was like, how does all my stars equal? And it's, oh, you're reaching out to create the base from which all stars are projected. And it creates one of these at every height. So like at every latitude, I would say, or even at every elevation. And now we have the, I think, cylindrical equivalent. No, this is conic section. So this is, oh, this is Cartesian. Regular coordinates, yeah. And then, so there we go, cylindrical. So again, this is transforming that data back and forth. It doesn't need to do sort of a projection. It just knows that, whatever the arc3 cosine of that value is my value for this value. And so it simultaneously exists in all of these frames. Yep. And then we got one more after this, I think, but I think we've seen enough spherical ones. This does it all the way through, I think. Yeah, so we just watched like every possible permutation of that coordinate system transform back and forth to and fro. So Cartesian simultaneity.
That's a good one.
Just came up with it just now. So spherical to Cartesian to cylindrical. There's a little bit of a difference because cylindrical has to go to another like rectangular coordinate for transfer technically, but yep. Absolutely, a spherical coordinate, right? So all the way around, make another circle, conic disk that way. Cool. Oh, no, there's another one? No, that's just cylindrical. We've already done that. Same basic stuff. Here's the kicker, though, is that they can all be endlessly translated to and from, back and forth all the way with literally no deviation, no hiccup, no nothing. It's just it exists, as a arctan or whatever, or as a tan negative 1 divided by x of this value. So that's something that we need. That's the only thing we need to take away from this math, is that all of these coordinate systems right here are equal. They're just preferential for how you want to display the current data set, that they can all equilaterally be used at any given point. So if, say, we're what's the curve distance here? Oh, we're going to take a tangent angle to the star. We're going to get this distance. What's the linear distance? Well, we're going to take a tangent angle to the star. We're going to get the same distance. Okay. All right. I got you. And that's why the celestial coordinate system and the geographical longitude and latitude and, right ascension and declination always match up. And that's why they appear curved, right? And spherically because of that. So the orthogonal coordinate is that's just an advanced way to accelerate one set of points where one point is constant, and they sort of get a way to look at the conical section that if it was constant. So that's how you get this shape, and that's just a way to display it. Same thing. So right here, again, they exist in all three. We just went over that. So they can represent the same point in three ways using Cartesian, cylindrical, and spherical. That is really the crux of it. And I know that if I put too much math, you guys will just check out. So let's roll right through that. I think we're done with math now. Just kidding, we have this one, angular distance. If angular size and distance, if you guys didn't know, that's where the where the tangent to the R over D comes from, where we invented the distance from to the horizon based on the Rayleigh's criterion and the drop rate. But that's based on angular size, and the tangent of theta is how we get, that measurement, really. So we're going to use that quite a bit. Here is one of the big problems of the geodesic longitude-latitude system created of big circles and circular arcs is that you always need to have this connector line, because you're assuming everything you do is curved, so you got to straighten it out and everything, and you got to find that straight line chord length between those arcs. This one, it turns out, let's see, this is based on a nautical mile and a statute mile. We took a arc length and chord relationship guess at, well, what if, let's just say that the linear distance would be, the chord would be longer. No, that would be shorter than the actual geodesic, right? So we would say 14 and 12. Now, is that going to be what the statute mile relationship is? Because I think it's 1.12 relationship. It's pretty close. But it turns out you can't ever actually get there. It's an integral limit, and it approaches but never reaches. And the chord arc length pair will never coincide. It just kind of bounces back and forth via a sine wave. I got a whole bunch of them and tried to graph it out, and that's what it does. So you can never find that. But this is the relationship of chord to arc. And what is, if you take a nautical mile and a statute mile, this is how different they are right here, and this is how different they are out here, essentially. That's what that shows. We're going to buzz right through the old stuff real quick. This is just one giant sheet. Essentially, it's the Amish created the help cheat sheet for the visual radius on the Excel sheet for the 69 miles per degree that we mapped out. But this is kind of like all of the formulas showing and how we computed and accommodated for everything: radius, rate, distance, diffraction, refraction, the light, wavelength, all that is in there, coefficient, etc. But all that to say, right, that we created a equivalent, an analog to what they had created, which is just a limit that's a spherical limit around us of that increment of radius. At 3959, so it's due to perspective, and we see the same distance in all the rays as we were showing by the spherical coordinate set. And of course, we also saw that when you're extending all of your distance at one r, one constant rate all around you in a circle, then all of your height will be capped. It'll all be capped at that level. Oops, this one. So you get that's why this circle here is 3959 over here, 2070 miles up here. It's getting sine of this function and cosine of this function to keep this going. And we're enforcing this. This is a unit circle enforcement here at 3959. This hypotenuse is being kind of tracked there to keep the limit of our view at visible limit, right? So below or above where we could resolve it before it becomes unresolvable. And all that results in is exactly as we see the world today, exactly as all the globers think they see the world, as half of the world around you that curves at the edges and that moves when you approach it or go away from it. That's what the phenomenon is that we all deal with every day. And they think that, oh, that's obviously because the Earth is a curved rate that no one's ever seen just beyond the edges of your view for no reason. And we're like, but maybe it's because of what all the other things that we see in the world do, and say when we go away from them, that they seem to recede proportionately into the distance. But no, it's curvature. But good thing we have this math over here to back up the optical nature of that radius and that limit, instead of it being a physical radius or limit. Now we have math to say, well, actually, it's almost certainly optics based in an optical drop rate and a disappearing bottom up necessity because of angular resolution and the bottom limit of the horizon being so much closer than the top. And then we have, I think, distance formula to get the curvature, a nice little applet. They say that the parabola doesn't work, but look how nice it fits, and then look how far it goes before it doesn't fit. It's retarded. People who have said that, you're all retarded, by the way. It's a parabola. Did you know that? Did you know it's a parabola? Oh, did I know that it scales exponentially, meaning that per foot is different and not a linear scale? I did know that. So then, how do we tell if it's, a flat plane with a curved visual limit of 3959 or a curved geodesic arc globe with the 3959 radius? That would be exactly the same way and seem exactly the same to us, right? Keeping in mind that would be like the breaking down version. All of these are identical from the viewer's perspective, right? From the person in the middle, it looks the same to them. Absolutely. Something that I wanted to point out, because it's hard to convince people when they're like, oh, it's my personal dome going to touch your personal dome, and you're like, okay, if I'm right, what do you think would change about how you see the world right now? And the answer is not at all, because I'm describing and actually stealing your entire perspective, and I'm just changing the mechanism. You jotted down curvature, I'm going to throw in some math. So when we did this, we used the unit circle. The right-hand side is the complicated unit circle, where you can get crazy with it. On the left is the easy unit circle, which we used. Instead of setting this to 1 to make all the 10 equal, we set it to 3959 and then offset it on every calculation so that we could enforce the unit circle with that radius. That's what that means. That's all that means when we were doing that. I don't know if we lost people there, but it was just making sure we have a visual limit and that it was enforced in a radius around us, essentially just like this. This is the unit circle going around every degree, every radian, every value to show what it would have been when we graphed it out, which is actually the next slide, I think, because it did show that. We did get that. Right, so just basic trig. So sine, cosine is all we did for a length and height, and then we enforced the hypotenuse of that basic triangle to be the visual radius, and that gets crab walked all the way through from zero from the North Pole to the equator, and that goes all the way down. I have a couple more, I think. Yeah, more of that, more data, more graphs from this project. I found the spreadsheet now. It's up, able to be downloaded if you guys want. This one is just a basic trend line and a basic, best fit function. It's got a, what do you call it? A regular polynomial line. Actual distance to apparent height. That looks pretty hunky-dory. The other one, though, of course, is the apparent to actual, I think. That's the one where it matters, right? Apparent, where we get this linear / logarithmic scaling trailing off function, which actually is the crux of everything, right? This right here is how we see the world. It's how we see distance. It's how we don't resolve past our limit. It's how that spherical Cartesian coordinate system enforces it says it breaks the ceiling height. It breaks the altitude limit. When you're converting it, that's one of the detriments. But that's because we can't actually resolve things past that limit beyond the ability of our optics to resolve it. It won't be resolved. But again, this is where they stop letting you use the correction tables. And if you're taking sights to stars or any celestial objects, you can do it up to about 72, 74 degrees, and then you have to correct after that. And you have to correct by the exact amount that it's not linear, it turns out. By this, so they correct it to bring it right back up to here to make it perfect, right? Knowing that it's not perfect and that nobody navigates down here. I had some fun with ChatGPT. It was like, hey, is it really linear 69 miles per degree all the way through? Absolutely, absolutely, yes. And I was like, okay, do me a favor, calculate what the distance would be at 0, 1, 2, and 3 degrees, and 89, 88, and 87 degrees. And what it did, sneaky, tricky little bastard that it is, was immediately did the backwards derived trigonomic cosine function to get it did like an offset to get the exact distance. And I was like, no. Use optics only, just what you can see, pretending you have a sextant and trig. And it's like, oh, well, it turns out that doesn't work and it's broken and it's not right and you're not right or anything and I'm not wrong, but it still says that, yeah. It's like, yeah, I know. So it's not linear. Though it's not linear all the time, it's not linear all the way. It's definitely breakable. So we have this, right? We have this limit we can look through. We can gauge. We can use linear distance scaling in this margin with more or less no problem. That's what it comes down to. You can't do the extremes. You can do basically everything above 25 and below 180-ish. You can go past that if you want to correct it, but then you're just going to correct to the sphericity as always, right? And again, it's not the logarithmic, but it is approaching a limit, logarithmic like. Let's see. So that they used this expression. They knew what they were doing. They stuck to the linear portion. They corrected what was not linear, and they let you think that little linear thing scaled infinitely, made light speed, took a 0.53 degree sun, and made a solar system based on a non-corruptible three-body problem solved. Don't worry, you've simplified it. It's been fixed. And also, everything has a mass distance that is covariantly scaled and perfect. Yeah, that's all based on nothing. So the last thing before we get into the cool shit is the apparent versus actual or true. Or it turns out every aspect of every part of celestial phenomenon, daily interaction, testing, you name it, is dealing with apparent. We only deal with apparent. We only have apparent. We only monitor apparent. We can only correct for apparent. There is nothing else. So I venture right here and now that there is no actual position of any of these stars. They only exist where you see them, and that's it. And that's all that we use, and that's all that we see, that's all that we can verify, and that's all that they see. So it seems to be that's the case. But they're going to still ask, well, how come it doesn't converge at the bottom of the ball when I look at the south and I see my optic convergence latitude dependent? It's like, yeah. So it says, yeah, this is just basically saying the same thing.
I'm trying to capture what the sun does, right, with the apparent position,
this is a good one.
Actual position, so to speak. And if we say that here, the sun is up here, right? This is the actual sun. We don't see it yet, but we're about to, right? Because it's about to sunrise, right? So it's not visible to us yet. We move it over, and now it's visible because it rose right here. So now we see it. This is literally at the horizon. So this is where we see it. If this distance all the way over here is actually 6,210, then it makes sense that we'd start to appear to see it here in its apparent position, right on the horizon, appearing to set. So it'll rise over us and then appear to set as it goes away, as it goes over us and then past us, right? So further away, and it's no longer visible. So
perfect. Apparent actual, there we go. So it says, yeah, turns out nobody uses actual. It doesn't exist, isn't a real thing. No one's ever referenced it, can't measure for it, never corrected it, never in an almanac. No one's ever took it. Like, it's only apparent, guys. So that's something to take away. When you're calculating position, you use the sextant, you make, your sight lines, you have corrections for human things, optics, refraction, all of that stuff. The thing that they get us with, though, is this shape right here. They're like, ha, you can't have all those same different latitude-dependent lines for one object. And it's like, oh, but we just said that there was no actual real thing for it to converge on, so that doesn't even make sense. But when we look at the sun, this is what we get all the time, right? Everyone gets... that's the maximum, I think, solstice height that we ever see it as, and then for its annual periodicity, and then it settles into right about here, and that's about where everyone sees it about that height all the time, everywhere. But it's where everyone else sees it. Actually, I saw a YouTube video today. Somebody modeled the sun with the personal grid with more than one observer, which is cool. I didn't see anyone do that before. I'll have to check that out and send it in the chat. And that shape that was just made, that Gleam made, is called an envelope, actually. It is a mathematical, I guess, I don't even know. I just thought it was cool. I didn't know it was a real thing. This is it's sort of an expression that is absolutely expected, mathematically feasible, and and sound, and not not made to look like, oh, well, you can't have that different angles depending on your distance. And it's like, well, no, you absolutely should have that. There's no other way you should have it. Back to our NASA backing up, and they're like, well, no one uses apparent. And it's like, well, only us and everyone in NASA. And it says, oh, maybe humans see the world in a flattened out dome or something. It makes sense. They seem closer when they're flying on the horizon, and they explain the supermoon. And you're like, oh, thanks for that direct quote, NASA. Appreciate the backup. Furthermore, right, we have our wonderful Gauss evidence when we did the paper and the non-Euclidean 3D space the way we see, when they did the tests and the sort of the vision depth when they were looking to see where it was most affected and what type of geometry would describe the near and far field. They had hyperbolic and which was negatively curved, and they had parabolic, I think. So this triangle is to represent where in our vision is skewed, and these little curved lines are exactly where, right in the middle, right where your eyes are, right in the front.
Using the equator and origin.
So now just, I think, a minute on solidifying, converting geographic to celestial.
Of each respective system. Now we can measure the angular position of any object in the sky relative to the equator, just like we would measure the coordinates of a location on Earth, with declination serving as the equivalent of latitude and right ascension serving as longitude.
Can be equally translated back and forth to and from with that 90-degree offset calculation that you can just get. It's all based on time. I didn't get that until like last night. I was like, oh, now I get it.
This analogy is also useful for explaining the dependence of the system's projection upon the latitude of the observer. The easiest way to visualize the projection at a given location is to imagine a line spanning from the center of the Earth to the location. Then imagine rotating the Earth so that the line is vertical. This is how.
Can we talk about your zodiac for a sec?
LOL.
Look over at the 9 o'clock and 10 o'clock positions, where you see Gemini as the crab and Cancer is the two girls. This zodiac is totally messed up.
Oh, dude, I got 30 of them.
You can
I
still
think
see it right under your cursor.
They're all fucked
Right
up.
under your
man.
cursor there on 9 o'clock.
What-
Gemini, and they show the crab, and then they have Cancer, and then they show the two Gemini symbols right there next to it at 10 o'clock.
What do you call a corrupted zodiac?
Yeah. Capricorn is the Taurus. Wicked.
Well, actually, I have a whole bunch of those. We'll get to that later. Yeah, that one is goofy as heck. They're supposed to come in an order and have 30 degrees of separation and be representative of the 12 winds, as far as I know. That's how I'm supposed to navigate with it. But what is this? Oh, getting into Geodesics. I think. Where this one. Right. Right, real quick. So before longitude, before they had the geographic necessity of a coordinate system that was inherently flawed and based on sphericity and measurements of the sky, they had the equinox, which was all they needed. Everyone got along fine for hundreds of years, knowing how to get, mark the sun at its highest point and then say that, okay, based on that, then the time for the longitude will be set. We have a zero, we have a basis for which to count, right? Latitude was fine, everything was fine, dead reckoning was fine. They had lunar transit, which was, basically watching the moon as it passed through static stars. They knew which stars it would pass through. They knew how long it would take. They could gauge time that way. And they could look at the moons of Jupiter, which had a similar periodicity over an annual period instead. So they were keeping track of time that way. They had all sorts of ways to do it. And I guess you could always just boil some water, as Alan said. So the equinox is a natural form of longitude, right? It's aligned with a specific meridian without the need for star navigation or GPS. And it says twice a year, you can, when the plane of Earth's equator passes through the center of the sun, or when the sun's ecliptic, moves over, it results in the sun being directly above the equator. And on that day, you can have equal length all over the world and set the zero for equal night, right? So it says the sun will cross, and you can make that local solar noon, and from there get all the correct measurements of time and convert into angular measurements for 15 degrees per hour. Off you go. No need for longitude, but then longitude, right? So This just goes over exactly how to do that if you wanted to. And I think we got one more cool video, and then we're going to solve it.
As cones here, since they are angles of declination, but since they are at a 90-degree angle relative to the celestial equator, they would be represented as infinitely thin lines. The complementary angle of declination is called the polar angle. It is represented by the interior angle of the cones and is used when converting between coordinate systems. The polar angle is measured relative to the plane of the poles to the cone's edge and is therefore equal to 90 minus the declination of any given cone.
Offset,
Since the celestial equator has a declination of 0, it's a great circle. Every other declination is represented by a minor circle with an apparent radius based on its angular position relative to the equators or poles. Basically, the apparent path of a star of a specific declination is determined by the angular distance of the declination from the equator. It also determines the angular radius of the circular path of the object as it completes a rotation around the axis of the poles. Here's an example of how the declination coordinate would appear to you if it were traced in the sky. The layout of the system in this example is based on my location in Florida at a latitude of about 27.3 degrees north, so we can see that the NCP is located at an altitude equal to that latitude. The declination coordinates are the circles radiating out from the NCP, just like the circles created by the cones representing declination on the example sphere. As time passes, watch how the stars stay fixed in their position relative to the circles of declination. This is why equatorial mounts are useful for long exposures. Since the declination of an object is constant, the mount only has to slew in one direction to compensate for the Earth's rotation.
So everyone knows, an equatorial mount, all that does is align with the motion of the sky. That's all it does. It has an actual alignment, and then it just tracks it all the way through. It follows it through the Earth. It pretends that it goes through the bottom of your feet when it goes out of your visible range. That's all.
Here's another view from the same latitude, this time looking west.
So
we can see the celestial to be represented as cones here, this time looking west.
Right here is pretty much how we manufacture sphericity, essentially. If all the curvature we see is the extremities of the limits of our vision, and then at the limit we have this line that never changes, that is measurable, called a latitude line or whatever line, and then we know that that marker has a circle, a concentric circle that goes out and comes back. And we assume, and then this is the crazy part, if you assume that when it's not there, it's below your feet through the bottom of a ball, it takes the exact same amount of time and space as if it was to go all the way around the circle Earth and come back to us. So this is the part.
We can see the celestial equator is separated from the prime vertical at an angle equal to the latitude, which is also equal to the altitude of the NCP. The declination coordinates in this view are the lines which are parallel to the equator. From this viewpoint, you'll notice that the declinations closer to the celestial equator have apparent angular radii which are much larger compared to the ones near the NCP. This is why they appear to be arcs when in fact they are actually circles like in the example sphere we saw earlier. Watch as time passes here, and again you'll see that the star's positions stay fixed relative to the declination circles. For a given interval of time, the stars with declinations closer to the celestial equator appear to move faster than those closer to the poles. This is due to the fact that the apparent angular radius of the paths of stars closer to the equator is larger. The difference
almost, guys, as if we see in a sphere, and at the limit, at the outer limit, it goes at a higher tangential velocity if it's spinning. Remember how they were like, oh, blue shift and red shift at the outer extremities? Then it's like, isn't that because it's going faster, or am I retarded? If you're retarded, am I retarded?
The difference in the apparent speeds of stars due to Earth's rotation is referred to as apparent angular velocity. The apparent angular velocity of a star is dependent upon the declination of the given star, and is measured relative to the observer at the center of the sphere.
That depends on the latitude. Depends how far away from it you are.
In terms of horizontal coordinates. Here's
back. Man, this came from Brian Leakey, I think, and this like changed my whole world. Cartesian to azimuthal coordinate transform from a set of coordinates that can simultaneously exist in two different coordinates. This kind of rocked my world. Let's go through it. What we have. So when it's in the azimuthal cylindrical conversion, everything remains the same azimuth wise. In the cylindrical thing, the coordinate gets represented as an angular dimension, but flattened out to face the cylinder. So the distance from the center is the latitude angle, essentially. So the height at which the circle slice is positioned is the cylindrical's vertical axis. So essentially, this thing gets created into this thing, and then this thing shoots up into infinite speeds of this thing. What every disk at every latitude is another disk with another set of these over here. It's a spherical to Cartesian simultaneity exist thing where it's not converted, you're not translating, you're not doing anything. You just, the math is you can do this or this. You can be helio or geocentric at any given point, wherever. No effort required. Right? Preserves properties, preserves everything. Coordinates are preserved. Latitude and longitude are preserved. Thank God. We need that. Spheres and shells about the origin become circles and disks. That's the real thing, right? So this becomes a disk. This becomes this. And then at every elevation all the way through is another one of these. And that's how we project it out. And that's how they do it. Altitude becomes apparent altitude as we put it in the spreadsheet and approaches a limit of unresolvability near the end of its linear line. So that's all that happens. Doesn't break, becomes the only thing that we've ever been able to use anyway. And this was the original form that I found it in before I messed with it. And so, yeah, so back to the spherical, just to point out the relationship between spherical Cartesian there is that we have the polar angle and the radial distance. The polar and spherical are analog because of the radial nature. They could just do from an angle and then just project outward the same at the same radius. So this is essentially the end result of that. It also says that as a result of this, at height 0, it'll be the center, but at around 6371 kilometers, which is exactly what we have 3959, will be the azimuthal projection of the flat Earth. And above that, all the celestial objects appear at their Cartesian distance from the center. So essentially, if they're all from that circle radius, they can't appear to be further than the maximum distance of your sphere. Makes sense to me. What's this one? Oh, it's the same one. Don't look at that zodiac either. I'm sure that one's perfect. So we have in the Cartesian coordinate system, you have all those 3 points, x, y, z, approaching 1 point, and the sphere represents all those points at the same distance r from the d from the radius, right? And that can be translated to latitude, and to get the angle from the horizontal plane of the azimuth, and that in that way you can get a 1-for-1 conversion to either of these at any given point for any space, right? So it means the distance is preserved, the height is preserved, the latitude is preserved, and apparent altitude becomes apparent altitude. Not a bad deal. Here's what it would look like, though, for real, when you do it all out. At every altitude, there's a disk, so you put another disk. I only put 3, but, you know, at every increment, you'd put a disk, and that disk would function of itself. The math would create, like, a permutation of itself at each level to accommodate what was before. Seems complicated when you look at it that way, but that's what it's doing, and in that way, you know, you can represent it perfectly. And then here we have my dolled up versions of each of these. We have what was the Cartesian and cylindrical, as of course being represented now is what I saw them as. You got planar Earth, and this was the infinite cylindrical celestial sky. So we exist over here. We see this. This goes with us. We travel with this, and then when we got to do stuff, we pretend to be over here. Right? Or yeah, I mean, the celestial sphere we have, but then we translate to planar Earth, but we do so in a fucked up way using spherical trigonometry. And people think that we don't, but we do use spherical trigonometry when we translate it to right ascension and declination. So you can look at an object, take an angle, and do it and get a distance. But to do something with that distance, once you have it, is where you're going to get into trouble to have to invoke that offset of the other axis from the polar coordinates, and that's definitely spherical trigonometry. So I made a couple of these. I wasn't sure which one I was going to go with for the proper celestial sphere emblem or whatever. Still undecided. And this is an example of how the celestial sphere would work, right? You have latitude dependent hemispherical sky. That's all it is. And that's what we have, right? That's what everyone observes. Latitude dependent sky. It's definitely easy to explain, and it works just like this, right? Up and down we go, and also like this.
Demonstration or model for a celestial sphere, and this one cuts it right in half because, of course, we only
Yep.
see the top half. and the top half is exactly equal to how long it takes the celestial object to rotate around the Earth and come back into our view. So let's start with this. We're gonna move our
Sound got low,
latitude.
homie.
Of course, as
Oh, man.
latitude dependency works, it's gonna put us say right at 20 degrees, and then we'll put the sun say over there, and your motion. Over
Yeah, I
there.
can't really hear the video.
Yeah, it's just the same thing we went through. Plus, we have this one. It's just a visual of the extended radius of the spherical limit, and then it being a sphere around you.
You froze up again.
Oh,
I'm blaming on the crappy Zodiac.
I have 33 more of them, though. Is that a bad number?
I don't know. Are they all crappy?
They're all beautiful. Cool looking backgrounds. Hey, do I have a celestial sphere here or what? What's going on? I don't. That's all right.
At least you're moving now.
Nice. This is you. This is how you see. This is what it looks like. I made that for Globers.
It makes me want to go pee.
Not a physical dome, right? Just the limit. It's just a quick on the celestial sphere. And it says, wow, a complete, logical, mathematically based, and biased sounded alternative for physical Earth curvature being the culprit. Right? Moving with you, moving against you, depending if you go, towards the rotation or against it, and that determines the movement. Super cool. Everybody is familiar. Right? You can look outside, that's what you see. And this is our wonderful diagram with the sine and the cosine and the measurements all in there. Whoa. Oh man, we need this visual. There we go. So this is supposed to emulate the sun taking the same amount of time to go around the Earth as it does to go through the bottom of a fake celestial sphere through your feet. If you imagine it and think about it real hard. Like if you, every time you don't see that sun, if you envision that it's going through your feet and coming around the circle radius to come back around for the next morning, that'll make it so, because that's all it takes. But I put 2 in, right? Because it's important to recognize that was bogarted, right? That timing of a circular orbit that comes, a half over here, half over there, mostly depending on the season, was bogarted to be like, oh, you know what that is? That's a sphere, and when you don't see it, it's below you, and also everywhere you're not seeing it's curving currently. Yep. Right, the local celestial sphere. I love it. What is this? I don't think that's anything. I think we got one more and we're done. Oh, we got one more and then one more section and we're done. Right, so there we go.
Did you cover the math yet?
Yeah, we did the coordinate systems.
Nice.
Did you already skip it?
No, I was just messing with you. That was awesome. It was a fantastic breakdown.
I tried to not go into it too much because I've been balls deep in that shit for 2 days, not gonna lie. Like I love it, so I didn't want to talk about it and have everyone sleep. Here's the important part. Here's where it's related, and we exist in simultaneity. Cool.
Yeah. No, the visuals were extremely helpful. Well done. Please continue.
This is the last part, I think, where it's just the linchpin on like if you weren't trying to combine a celestial sphere to a geoid, why would you do all of the things that would be number one to combine the geoid? And then, like, why would you do astrogeodetics? Why would you align to the thing? Why would you make it dependent on the celestial observation? Why is it always latitude dependent?
Equator-centric systems. You can imagine overlaying the spherical projection of the sky onto the Earth, aligning the two using the equator and origin of each respective system. Now we can measure the angular position of any object in the sky relative to the equator, just like we would measure the coordinates of a location on Earth, with declination serving as the equivalent of latitude and right ascension serving as longitude. This analogy is also useful for explaining the dependence of the system's projection upon the latitude of the observer. The easiest way to visualize the projection at a given location is to imagine a line spanning from the center of the Earth to the location. Then imagine rotating the Earth so that the line is vertical. This is how the system will appear at the given location, with the horizon being perpendicular to the imaginary line. For instance, if we are located along the terrestrial equator, then the celestial equator will be directly above our heads, spanning east to west.
Look at that celestial. Look at that celestial sphere right on top of that geoid, man. It's almost like you can't tell them apart.
The celestial pole is located directly on the horizon. If we are located at a latitude of 30 degrees north, then the celestial equator will be tilted 30 degrees to the south, with the north celestial pole having an altitude of 30 degrees and the south celestial pole having an altitude of negative 30 degrees. If we were instead located at a latitude of 30 degrees south, then the opposite rotation would occur. The equator would be tilted 30 degrees to the north, the south celestial pole would have an altitude of 30 degrees, and the north celestial pole would have an altitude of negative 30 degrees. Overall, the functionality of the two systems are similar. Basically, an equatorial mount is just a horizontal mount tilted at an angle.
Right. So we're trying to combine the coordinate system. We want to make them match. The question though is why? Like, why would you want to do that? Oh, so you have like a geoid and an ellipsoid. That's definitely not the stars. They're two different competing concurrent models of the same thing that we like to keep around for whatever reason. And then we like to make corrections that get these closer together, and we want these points to just get as close together as we can to make sure that they're the same. That's helpful for us, I think. So they have astronomic latitude, they have geodetic latitude, they have geographic latitude, they have astronomical latitude, they have everything. Like, this is all the coordinate systems that they dick around with to pretend that the Earth isn't flat.
Yeah, could you go back a slide?
Yeah.
What is geoid undulation?
So that's when they have to keep deflecting it all the time. It's like they keep flicking the bean, and it just kind of vibrates after a while. You know what I mean?
No.
It's literally when they keep making corrections to it, they say it's undulating. I think.
No way, dude. So when you're deflecting your verti and you can't get the measurements you need, you're undulating.
Yeah, undulating it hard.
No, bro.
I think.
Okay.
That's I just read that before.
Stone, hit me with a deflect as they please, bro. I didn't know I didn't know they were undulating as they please as well, dude. That's crazy.
Shrink to fit.
Oh my goodness.
I can do it, guys. I can do everything.
Kicking ass. Kicking major ass.
Oh crap. Well, that wasn't. Yeah, I guess that was it. Let's go back to those two slides. This one, astrogeodetic, gravimetric, dynamic. These are good words. The techniques for vertical and geoid separation. We got to make sure that depending on our choice, we deflect that vertical, get that into the corrections book for the astronomical and the ephemeris, and make sure that the geoid gets matched to the celestial sphere. So now that I'm all the way through it, that I had to do geodesic surveying and the things, the longitude history to get the understanding of what the heck is going on with the sky. It's like, but you were doing it all along, right in our faces. No one even knew what it meant, and you just made everything equal the celestial sphere. If you look up the actual history, which is just like if you get past the Wikipedia lie to you history about everything, then people were making star maps way before they were making land maps, and star maps are the only thing that people care about. And it turns out that's a good thing, because stars are the reason for our maps, are the markers for the longitude, are the zero markers, are the way we count, and without which we wouldn't be able to do anything. So to have a flat Earth movement without looking at the sky is more than retarded, I think. I think this is the last one. So the transformation.
Are you telling me that we all need to get familiar with a compass and a square?
Yes, and definitely the compass.
Word.
Since we're probably good with the square.
Yeah, we seem to have the square covered, huh?
Yeah, we should practice with the compass. So I think I had another one I was looking for that I don't see, that literally shows everything. Oh, there it is. So like the point. It says the point of everything. The deflection of the vertical has primary purposes. the transformation of astronomical coordinates to geodetic coordinates. Okay. The conversion of astronomic azimuth to geodetic azimuth. Interesting. And the reduction of vertical horizontal angles to the spheroid. What do you guys think of that?
No way. Just in plain English, huh? Hold on 1 second. Let me take a screenshot of that slide. Actually, just send it to me. Then when you're done. That's crazy.
You get the whole deck.
Yeah.
160 slides.
So as we describe the deflection of the vertical, and they're like, nuh-uh. That's literally exactly 1-to-1 what its purpose is. It's to make the sky match, or to make the ground match the sky.
It's to create a map out of the sky. Yeah, essentially, right? Like all we know about is the stars. So you want to live in a ball? Well, the stars are kind of, because we see in a curved nature, they were able to make the world curve. It's crazy, man.
Yeah.
Crazy.
I'm thinking somebody was a little bit hasty putting this final slide together.
Oh yeah, dude, the whole thing is hasty. Why? What gave it away? Should I get off it? Hold on. Let's go to the next one.
The missing vowel.
Oh yeah, bank. Yeah. How about
Yeah.
How about this one? Is this one better?
That's decent.
Well, the complete absence of any glyphs whatsoever. Yeah, I'd say better.
Glyphs. That's a good word for it.
Hold on, can we get some AI music in the background while we're talking?
Yeah. Hold on, let me put it up super loud. Give me 1 second.
No. All right, I muted it.
All this stuff is
God bless.
Thank God I know how to get arctans, man, from this one little slide. We can just get like one over, because like one of the people on Clubhouse was like, you can't get the radius of with radius criterion and anything. I'll quit my channel right now if you can. I was like, oh, all right, hold my beer. Let me go get the recorder. Let me get over there. And the dude just like lost his shit every step of the way. He was like, all right, so start with it. He's like, no, you can't. Like every step. But then like I got him to calculate. I told him what to do and he calculated it. And then he just like nah and braid and he paused for 2 hours and left. And I was like, that was satisfying, I guess. I don't know what I thought would happen.
Nice. Shout out to the lads over there on, what was that called? Cabin?
Clubhouse.
Clubhouse.
Cabin?
Clubhouse.
Dude, that was way off.
That was awesome, Shane. Nice job, man.
Nice. Thanks, dude.
Yeah, fantastic presentation and breakdown of the coordinate systems and the transformations therein, and how the what did you call it? Cartesian simultaneity.
That's a good term, dude.
Where they're all equivalent, all at the same time.
Yeah, think about it. Couldn't be any other way. It's like, oh, I'm going to convert this to the spheroid real quick and get my geodesic on my WGS84 equivalent before I bring it back to my flattened out geodesic linear longitude line. Like, what? No, you just exist everywhere all at once, homie. Stop it.
Yeah.
Or rather, you exist in all the frames that we made up for you to exist in.
So many good visuals.
Yeah,
I think you really illustrated your point really well, and you really illustrated like, oh look, when we took everything that was mapped to a globe, and then we transformed it to fit it to a circle, and then the distances didn't match the globe. We got you. It's like, oh, yeah. Well, turns out your globe was, like your circle map was not a properly mapped. Like it's not proportional to the ground beneath your feet. It's just literally a sphere that's been stretched out into a circle. So you have a malformed map.
Well, yeah, right. Because that's what the Gleason is. It's just it takes a intact, proportionate coordinate set, and it warps the shit out of it to stretch it into a disc like that. And it's like cool, but you can't be stretched unless you're a pre-spheroidal man. So.
Well, like I say, when they tell us, where's your map, flat earther, I like to say, well, sure, give me like a couple hundred years, decree from the king, the royal, like a fleet of ships from the Royal Society, and a bunch of, at the time, state of the art magnetometers and such, and then maybe I'll give you a map.
At this point, I think we just need like people to go in the south, and we can do everything. Because wait for an equinox, grab a thing, take the sun, do a margin, give me a latitude down to the degree, and then just push it out, right? Because do we want to have a sky map based on the sun as well? How else would you derive longitude, I guess, or latitude?
Good idea, Shane. And you could call it the final experiment, and you could hide your identity until revealing yourself. You could send people invitations with golden tickets.
Could I?
There must be Oompa Loompas,
What time is it? How long was that?
or the plan just won't work.
That was a clean 2-hour piece.
Oh, way longer. I thought it was only an hour. All right. All right. So yeah, that's a lot of slides. Let me. Dude, you see this meme? Somebody literally put that out as like a gotcha on our timeline, and I was like, "Ooh, I'm gonna save that for a lesson." You're an
Dude,
idiot.
yeah. Dude, there's literally plane flight transformation lads that are like, why doesn't it match Flurfer?
And I'm like, guess what? It does.
All over the timeline, and they never stop. Like, you know, you've been kind of saying this for a hot minute, and it's still like their go-to, you know, side piece argument that they can't quit.
Yeah, like imagine you're having fun with a thing,
Right.
And then someone comes along, kicks that thing away, and you're like,
Yeah.
I want that thing back, though. I want to have something.
Yeah. Yeah, it turns
They're
out they
just
were all the
sad.
same always. Unlucky.
Yeah. Yeah.
Don't worry, bros. They got us too. You know, no worries.
So yeah, anyone else have any other questions, thoughts? Shane, any other final thoughts?
I have a whole other presentation on just the math. That's probably just for me because nobody gives a shit. But it's pretty sweet. It's like 90 slides deep.
I mean, you should still do it.
And then I have a whole nother Gleason's presentation about 100 slides deep.
Nice.
Just on Gleason's map and images and whatever. Yeah, Canva.
Sounds awesome. So there you go. Look forward to those someday in the future. Cool. Well, let's go ahead and wrap up streams then.
All right,
Nice.
Toby, you want to close this out for the week?
Yeah, sounds good. So yeah, thanks everyone for tuning in for Aether Roundtable number 31, Sky Miles, presented by Shane. And we learned about all the different ways that sky observations can be transformed and the way in which the spherical coordinate system that they give us can be clearly transformed onto a planar coordinate system in a coherent way. So thank you very much to Shane for that, and hopefully we can continue this discussion going into the future here. And so yeah, tomorrow night, tune in for reading night at 9 p.m. Eastern. We will be jumping into right back into Shankar's physics. This will be the third night in a row we'll be doing that. We'll be on chapter 4 about Newton. We may deviate from Shankar in coming nights, maybe even tomorrow night. I mean, we'll still read Shankar tomorrow night for sure, but I don't want to get stuck on just this book forever. I want to do some other readings as well. Especially Dr. Bennett just dropped a paper about the Sagnac effect that I would really like for us to read. So maybe we can squeeze that in tomorrow or next week.
Yes.
And then Friday, tune in for Flat Earth Fridays episode number 100, hosted by Proud and Sacred. Check that out. And yeah, thanks again, everyone, for being here. Tune on in for more stuff coming up this week, next week. Take care.